Thank you, Ginger. I don't know if that's actually going to be the case, but I can hope. This is the art and science of vulnerability. I don't intend it for it to be too much of a rant, but it probably will get a little bit ranty at some point. Just as a voice check, can everybody hear me okay? All right, thank you. So as any great presentation, ideally I'm going to tell you everything I'm going to tell you right at the very beginning, and then we're going to actually tell you that to you, and then I'll tell it to you again at the end. Ultimately, this talk, in terms of the art and science of vulnerability, is a rant against the term cyber, because cyber hides all sorts of sins. Cyber is magic. Cyber is people in black hoodies sitting in basements hacking you from wherever. It's weird things happening to your phone. It's nation states hacking your industrial control systems. It is the multi-trillion-dollar industry that a lot of people benefit from, not all of which are the people that it is aiming to protect or the people who are doing the malicious actions. So that's really the overall point, is that when we're talking about vulnerability, when we're talking about cyber, like these things actually mean something. They have real world implications. You can reason about it. It's not magic, but it also is not something that is just easily solvable, because in addition to being something that is not magic, there is an art to it. So again, the art and science of vulnerability. So first off, who is Rob? I'm Robert Erbes. Provided a little phonetic display of how to pronounce my last name, because when I actually came to Idaho, which was around 2008, and started working at the Idaho National Lab, I didn't feel like correcting people on how to pronounce my last name. And so there's about 15 different ways to pronounce my last name that are in common use. This is the only one that I actually use, but that's fine. As far as my background, well, actually first, would the audience please raise your hand if you've known or have worked with me? Okay, so that's about half the audience. So a lot of this is a little bit weird because I'm talking to my friends and sometimes family. But for everybody else's benefit, a little bit of background about me. I'm going to go back to the school days. So, because some people are at least around school age. So I got a bachelor's degree in information technology from New Mexico Tech, which is a very small school in Socorro, New Mexico. Had about 1,200 students total. My first year of tuition cost $800. My degree was in, I think I just mentioned, information technology, which is weird because I have an IT degree for my bachelor's. And what that meant at the time was that instead of taking compilers, I took binary exploitation. Instead of taking principles of programming languages, I took digital forensics. So it was basically trying to put a polite veneer over, we're going to train people how to do information security without calling it cybersecurity degree. So this is a time when you didn't have computer security degrees at all. I did do the scholarship for service. I was one of the first people to go through that at New Mexico Tech because the program had just started. And as part of that, I got a master's degree in computer science with a focus in information technology again. Mostly what I focused on was digital forensics. But I was also particularly interested in ICS, Industrial Control System Security, because I'm interested primarily in complexity, the way that very simple systems can interact with each other and create weird emergent behaviors. I don't actually care about physical stuff that very much, or ICS. I care about weird interactions of things. So after that, as part of the scholarship for service, I got a job with the federal government working for the Army as an Army civilian. And I did that at White Sands Missile Range for 3 years, and mostly what I did was a little bit of hacking, a little bit of actually assessing real systems that were in development, but a lot of paper exercises where the Army was saying, hey, we know people get hacked all the time. We need to start building this security and evaluating the security at the very beginning. We need to start right now. And so I did a lot of vulnerability analysis on systems that did not exist yet, which I can tell you is actually both either really, really easy, because you just say, I found all the vulnerabilities and nobody can tell you you did otherwise, or it's really hard because the system doesn't exist and you don't know where the vulnerabilities are, because the devils are in the details. The second thing that I did was a lot of modeling and simulation. So they were modeling things like network attacks. So if you can model a network, you can model the resources of the network. That means that you actually have something that you can model. And they wanted me to try to implement a model of a Stack Overflow. And I was like, I can model that, but it doesn't tell you anything because it's just the thing that happens. There's no point in modeling it. Okay, so then I got a call from one of my friends who said, hey, do you want to move to Idaho? And I said, where's Idaho? Because I didn't know. And they were calling from the National Lab, who they had gotten a job up here. And so I came up here and started working for the Idaho National Lab, doing a lot of vulnerability assessments of SCADA systems. So I was doing something, participating in the National SCADA Testbed. I did that for about 5 years, and along that time, I was part of a group of other people at Idaho National Lab and outside the lab that won the DEF CON CTF, so I got a black badge from that. And as part of doing that, I also got to talk to a lot of consultants and private companies, and then went and left the lab, went and worked for IOActive for 3 years, and then a company called Praetorian for another 2 years, both security consulting companies. And during that time, I basically spent anywhere from a week to 3-month term gigs, where every single time I had to pick up a new technology, understand how it worked, and then figure out how to break it. So I did that for about 5 years in total, got really tired of doing that, and said, I need an easier job, so I came back to the National Lab. So I've now been back to the National Lab for about 5 years. Overall, I've got about 20 years experience, ultimately doing vulnerability research, which is what this is all about. I do consider myself an expert in vulnerability research. That does not mean I can break everything, but it does mean that I do think I understand it really well. Okay, so first thing, always start with a contest. So here's the contest. I want everybody, first person to shout out the line number of the vulnerability wins. Ready? Spot the vulnerability. Go. Okay, who got it? Just kidding. All right, now we'll actually do it. Just shout out the line of the vulnerability. And this is C code. If you don't know C, don't worry about it. Wait for somebody else to yell it. It's written in C. That's the problem. 23. Okay, so what's happening on line 23? We got a stir copy. Okay, so we're going to talk about what this means for people who don't understand C. We'll talk about this a little bit. We have a main function. This is just a function that gets called by the operating system. It provides an argument count and an argument vector. The actual arguments that are provided to the program. The very first arguments, the very first string in the argument vector is going to be the name of the program that you actually executed, and then everything after that is the arguments. If the number of arguments provided is greater than 1, meaning we executed it with more than one argument, then it's going to call this function called do the overflow with that first argument. So we can actually see that if I call the function without an argument, it's going to say, hey, I can't do an overflow if you didn't give me anything. That makes pretty good sense. So then we go back. If we do actually call the argument, again, it's going to pass that pointer to that first string, and it's called do the overflow. It's going to define a statically allocated buffer of 8 characters long. And this is statically allocated. It exists on the stack. It's known about at compile time. And in very good C coding behavior, I'm not going to assume the state of that particular buffer. It could have anything in it, so I'm going to set it all to zeros. And then I'm going to do this operation called the stir copy, which is a function. And what that function does is that it takes this string, the source, and copies it over to the destination here. So in C, strings are delimited. So the end of a string is delimited and indicated by a null byte. So if you're copying over something, you know that you've reached the end of the string as soon as you reach a 0. And in this case, that's exactly what happens. It'll copy over until it reaches a 0, and then it will stop. And then it's going to print out, via this printf function, you tried, and it's going to print out the value. This is the format. This says printed out as a string, as opposed to an integer or any other type. And it's going to print out the string that we just copied it into. So if we do that here, we provide do the overflow, A, B, B, C, C, D, D, and it just prints back what we did. So the question is, what happens if we provide more than 8 bytes? And actually, if I'm being pedantic, I would say that, yeah, that's right. I would say that there's also kind of technically a vulnerability, or at least a bug on line 21. Because again, if C strings are null terminated, then if we write and fill up that entire buffer of 8 characters and we don't leave space for a null, if there's junk after that, then it's just going to keep going and printing it out. But that is less likely to happen, but it is a bug. Okay, so this is what happens when you run it with too many characters. We use the classic capital A to fill a buffer for identifying Stack Overflow. And indeed, actually, it even works. So even though there was too many characters in there, it did the you tried, and it printed back that entire thing. So we overflowed a buffer, but the program was still running. And it's only when it tried to return that it crashed. And in this case, it didn't quite crash, because there's operating system protections, there's compiler protections that have been built into this. This is just the default compiler in Ubuntu. And we have all these mitigations for this kind of thing now. And if I don't take account of those mitigations in my exploitation attempt, then nothing's going to happen. And in fact, this is exactly that. So there's some science here in that we are able to detect the attack, we're able to automatically abort the program, and we handle it gracefully, as opposed to going off into la la land. Okay, so that's an overflow. By show of hands, was that a vulnerability? Raise your hand if you say yes. A lot of, I think that's good. Raise your hand if you say no. Okay, a lot of unsures. That's pretty good. I guess that's why you're on this talk. The answer is no, that is not a vulnerability. It is a buffer overflow, but it's not a vulnerability. Why? Well, quite frankly, it's not a vulnerability because it doesn't cross any sort of security boundary. So if I have this nice little C program, and I'm able to run the C program and provide input to that C program, and I get code execution, I've just gotten code execution in the same context that I was in order to run the program. I, the user, can run code on my computer. I ran that code on that computer, and I was still able to run code. Nothing changed. Not a vulnerability. So now the question, well, what if it was an echo server on a network? So same idea, but instead of taking input from the command line, it had open ports, and I could send a message to it, and that would overflow over a network. Well, kind of not really still, because we've still gone from, I mean, there's room for that. If somebody else is on my network, and they were to talk to this thing and do the overflow and get code execution, that could definitely be a vulnerability, but we don't know that that's actually what's going to happen. I could have this running on my home network forever, and nobody could ever talk to it, because I don't let them. Well, what if it was an echo server on a public network? So not just my home network, but a network available to the entire internet. Yeah, we're definitely getting there. So I think that's pretty good. Again, we're just able to run code in the context of the normal user. But what if it was running as root on a public network? Now we're talking seriousness, and that's definitely going to be remote code execution. As root, I think we've got our vulnerability. We should contact somebody and text the CVE numbering authority. And so we do that. So give me my CVE. And they say no. Why would they say no? Well, quite frankly, because I just wrote a dumb program. I called it do the overflow. If I contact the CNA and say, hey, I want my CVE for this program I just wrote, it's got a vulnerability in it, I would hope that they would say no, or at least, who uses that program? Where is it from? Did you just do that yourself? And I think that there's a little bit more going on. So, I mean, we're definitely reached the vulnerability stage yet, but the CNA is going to hopefully say no. Well, why not? Obviously, there has to be something else going on here. It's not just a matter of buffer overflows or any other kind of bug. And that's what we're talking about, implicit security boundaries versus explicit security boundaries. When you hear about a vulnerability, you often think, well, that's just a vulnerability. Somebody identified it, somebody's able to exploit it. That's it, we're done. But it ignores the fact that somebody did have to do that. When I talk buffer overflow, I'm talking about an implicit security boundary that something is being exploited, something's happening. I've gone from just being able to send data to a computer to having that computer run it for me. It's remote code execution. It changes context. And I think a lot of people forget that there's this idea in computers of process separation, that I shouldn't just run any code that I give you, that there's something else going on. There's this implicit security boundary. And that gets hidden a lot when you talk about vulnerabilities. When I say, oh, I've got the CVE and whatever, you're like, oh, that's definitely a vulnerability. It's definitely crossing some security boundary. But really, they might just be talking about a buffer overflow. Not all buffer overflows are vulnerabilities. And as far as the picture goes, if you ask Google, show me a picture for implicit security boundaries, it comes back with this. I don't know why. AI will save us all. So now we're talking the opposite of the implicit security boundary is the explicit security boundary. And again, this is what Google gave me when I said, show me explicit security boundaries. Here we go. That's your explicit security boundary. But it's the idea of something that is very explicit. Like security means something. I'll get to it at the end as well, is that you're never just secure. Like you're always secure against a very particular threat. So an explicit security boundary would be, I only want people named Dave to be able to run code on my computer. So I might have a check about that. And I'll say, what's your name? And if you say Dave, welcome in. If you say Rob, I'm going to say no. And if you're able to bypass that, I set up an explicit security boundary, an area of authorization in the world where I want something to happen, and I want to protect it from not happening. And then if you can cross that, that's a pretty explicit boundary. I've drawn a line in the sand, and I said, you cross this line, you die. And then you cross the line, and then maybe I'll do it again a few hundred other times. But the idea is sometimes we have these implicit security boundaries, but more often we have these explicit security boundaries, and it's very important to know which one you're dealing with. Case in point, this is a web browser, or at least a picture of a web browser, accessing EFF.org, which is an excellent organization. I am a contributing member, but I have no other relationship to them. But when you're talking about code execution and remote code execution, you know what browsers are? They're little remote code execution machines, where you ask a server for some code, they send it to you, and you execute it every single time. And the entire security model of the web is built up entirely different from binary security models. It's not a matter of can I run this code or not, it's a matter of where did this code come from? Did it come from a place that I meant it to come from? It's all based on this idea of a single origin policy, and it's complicated and convoluted as all get out. And you can tell that because in the past 25 years, as the web started to catch on, we keep learning all sorts of new vulnerabilities, new classes of vulnerabilities, new context-aware things, new ways of getting exploited, new ways of leaking data, new ways of ruining your life. And this is all because it's an entirely different security model. It's different security boundaries. Instead of having buffer overflows, you have server-side request forgeries. Instead of having integer overflows, you have cross-site scripting. Like entirely new technologies, almost all of it is completely not memory safety. It's all about the context and the security model that you're dealing with. It's a little bit more explicit, like this whole certificate thing. I can't show you my mouse. Little lockbox next to the EFF.org on the top that tells you that you're secure. Like there's a whole cryptographic regime associated with establishing identity, of showing that you are talking to who you think you're talking to. But even then, all that's just kind of like this technical underpinning of what is ultimately like a social idea of I'm talking to the EFF, and the EFF, I believe, has access to this domain, and that I trust that all the cryptographic mechanisms that go to identify that EFF is who they say they are working, that somebody at some other certificate authority didn't produce a certificate for EFF that indicates that, no, they're really EFF, and that when they redirect my traffic to them, that I'm not having an issue. So there's all sorts of social things on the background, but ultimately, again, context and the implicit versus explicit security boundary, running code on somebody else's computer is not always a vulnerability. Sometimes you explicitly need to do that. So now we're getting into the science. So I mentioned my background and kind of my school because it was very much a big research topic in the very early 2000s and even the early 1990s to develop taxonomies of vulnerabilities. Like we know that these things exist. The first part of science is to basically survey the world and start categorizing and building things up. So they said, okay, we're going to develop these cool things called common weakness enumerations or common vulnerability enumerations, and just start to get a survey of what the world is. And you do that so that we can then predict, explain, detect, and ultimately prevent. So if we can understand a category of vulnerability, then we can do something about it, we can study it, we can create mitigations against it. And indeed, that's actually very much what happened over the next 25 years, even before that. Again, we saw at the very beginning of this presentation, we have this buffer overflow. Unmitigated or without extra work from the attacker, it's completely mitigated by detections that have been put in place by people who have studied buffer overflows, who understand the problem, who know that we're talking about let's get these two up. We're talking about a von Neumann machine that can mix up data and code in the same memory space so that when I override a little bit of the data part, I can also influence the code part, and they're not completely separated. In other computer architectures, apologize for my voice, but it's, we can do these things, we can come up with mitigations. And this, again, goes back quite a bit. So I mentioned that I took a course called Binary Exploitation. This was the course material for that. And the early days was kind of weird. So this is Aleph 1's famous hacking the stack, or smashing the stack for fun and profit. I'm going to read that little box for you because I think it's interesting and kind of archaic. So they say, smash the stack in C programming. On many C implementations, it is possible to corrupt the execution stack by writing past the end of an array declared auto in a routine. I actually don't know what it means to declare something auto in a routine. I guess I meant something at the time. It means a stack. Yeah, see, we just call it the stack now, but to declare something auto, I called it statically allocated buffer. Anyway, so code that does this is said to smash the stack and can cause return from the routine to jump to a random address. I think that's interesting because I don't care about it jumping to a random address when I'm trying to get code execution. I want it to jump to a very specific address, the one that my code that I supplied lives at. This can produce some of the most insidious data-dependent bugs known to mankind. Variants include trash the stack, scribble the stack, mangle the stack. The term mung the stack is not used as this is never done intentionally. See spam. So it's interesting that we have all these different categorizations, and this is really the crystallization and publishing in Frac of this idea to make it widely available. It obviously existed for several years before this, maybe even decades. It definitely existed for multiple decades before this, just by accident. You write some bad code, you make some bad assumptions, somebody overflows the buffer, now your program crashes, oh darn, that was a bug. But again, this has been done for a long time. And it's not just buffer overflows that are this well understood. We also really, really understand all kinds of other computery things like integer overflows. So integer overflows are something that happens when a register overflows the amount of space that it has to hold information. And these are actually a good source of vulnerabilities, and they're really easy to find. You just have to look for a place where math is happening using a user-controlled value, and voila, you have integer overflows. Finding these things is so easy, you can teach this to a child. In fact, you all know how to find integer overflows. You found integer overflows as one of the very first things you did when you learned to count. Because in addition to registers only having 8 bits at a time, your 8-bit Nintendo Entertainment System, if you ever had one, only had 8-bit registers, and so we only hold 8 bits worth of information in one of those registers. We only have 10 fingers. We can only hold 10 numbers on our fingers before we overflow that buffer. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We're out of numbers. We wrap around. That's integer overflow. And literally, you teach this to a child. And in fact, I did teach this to my daughter's class. I think she was in 2nd grade. I taught binary math because it is just a different number system. You go 1, 2, 3, 4, and you keep going. I did the binary wrong in my hand, so don't pay attention to that part. But it was, it's easy when you think about it. And this is like a source of huge number of vulnerabilities. But again, conceptually, it's not bad. But the thing is that with all these vulnerabilities and all these vulnerability classes that we understand and we do the science on, the bugs keep happening, along with another 600-ish categories identified by the CWE. And this is not knocking the CWE in any way. These are all different types of weaknesses, common weakness enumeration. They exist, they are identified, new ones are identified all the time because new systems are being identified all the time. Computers are arbitrary, and computers are dumb, and they do whatever we ask them to do. So the classification is instructed, but again, there's something else going on. So if it's not the weaknesses that cause the vulnerability, what is it? You'll remember, we said, hey, I've got this vulnerability. It's got a buffer overflow. I want the CNA to give me my CVE so that I can do delete speak and like brag about it, or spruce up my resume as a vulnerability hunter or researcher. And they said no. So the question is, what makes a vulnerability? Well, obviously, if you have that CVE, somebody has done the hard work at figuring it out. So if I got that CVE, that must be the vulnerability. Or not. I just like this GIF. I give you CVE 2020-19909. So this was disclosed, well, actually in 2020, because that's how CVEs work. But this is a little story that I'm going to have Daniel, one of the core authors, if not the core author of the curl library, kind of talk about. And we're going to go along on this little journey. So on August 25th, you got an email from a user who said, hey, I wanted to let you know that there's some recent curl CVE published, and it doesn't look like it was acknowledged by you guys since it's not mentioned on your website. It's CVE 2020-19909, and Daniel can't tell who filed it. They just know that it's there. And that's weird because they own all their curl issues. They actually publish all the security information on their website. They're very responsible because they know it's used in a lot of places and they do due diligence. So again, they list over 140 of their vulnerabilities with every possible detail about what it is. It's an open source project. You can learn from it. It's great. And now somebody else has suddenly submitted a CVE for curl. That's a surprise. they would have preferred that they told them about it so they could fix it, or do something about it, or at least explain what's going on, but that wasn't done. So what is the CVE? So they go and look for the CVE and get the National Vulnerability Database, and they find this small description. It's an integer overflow vulnerability in tool_operate.c in curl 765.2 via crafted value as a retry delay. And now the crazy part. They gave it a 9.8 critical out of a possible 10 on the CVSS scale. So CVSS is the Common Vulnerability Scoring System. Yeah, we'll call it that. Ultimately, it's a means of trying to communicate the severity of a vulnerability once it's been identified. It includes information about, like, what do you have to do to access it? Where do you have to be? Can you talk to this vulnerability over a network? Do you have to be in an adjacent network, like actually physically kind of plugged into it? Or do you have to be physically present to it? Like, this computer has a very physical vulnerability in that I can take a hammer to it, and I've got a really effective denial of service attack. And in fact, that might be something that I'd have a CVSS score for. Then the other component is, like, how hard is it to get to? You have to have somebody authenticated. You have to have some sort of credentials. What is the overall severity of the effect? Are you affecting availability, integrity, confidentiality? If so, how much? All these things go into a CVSS base score. The worst possible base score, like the world is ending, the sky is falling, is a 10. So we've got this integer overflow that's being graded as a 9.8. That's really bad. It means you have an unauthenticated attacker who can do things without any real complexity. So it's not a hard attack to do, and it has complete integrity, availability, and confidentiality effects. It changes the scope. It's all kinds of bad stuff. So I'll get a little bit more background and talk more about what this vulnerability is. So in 2019, an individual posted an issue on HackerOne where they said that the curl's --retry delay command line option had an integer overflow. What's actually happening is that, as it says here, the option accepts a number of seconds and then internally converts 2 milliseconds by multiplying the value by 1,000. So it sets how long curl should wait until it makes a retry if the previous transfer failed with a transient error. So that means on a 64-bit machine, if you do a curl retry in a very large number, it's going to multiply that very large number by 1,000. It's going to cause an integer overflow on a 64-bit machine. And now curl will wait approximately 384 seconds instead of more seconds than there are to reach the heat depth of the universe. On a Windows machine which has 32-bit longs, you can basically, it would ultimately result in about 25 days of retry delay. So it's a pretty trivial integer overflow. Again, this retry delay is saying, I want to make a request. If I don't succeed, wait a certain amount of time before I make the request again. And this is saying if you provided a really big value, longer than the heat depth of the universe, then it's going to overflow and you're going to wait less time before you make another request. It's definitely a bug. Is it a security problem? Absolutely not. So they told the individual that and then fixed it, and everything's great. Released in curl 766.0. So as Daniel's complaining about this and talking about it on his blog, some people mentioned that, hey, it's technically undefined behavior if you do this integer overflow, and really all bets are off. So there could be a security issue there. And he says that he's not a fan of philosophical thought exercises around vulnerabilities. And I thought that's good because that's really all I'm doing today is giving a philosophical talk about vulnerabilities. And ultimately, what he says is that it's kind of pointless. It's easy to test these things. You say it's a vulnerability, I say it's not. We can just test it. Like, we'll just run the test, and then we know. And ultimately, we don't have to worry about these like really weird unknowns of technically undefined behaviors. It is unexpected behavior. It is a silly bug, but it's definitely not a security flaw. So he sent a message to MITRE, who's the ultimate caretaker, is his understanding of who the ultimate caretaker of the CVE database is, saying, hey, I want you to reject this because it's not a security issue. And MITRE responded and said, well, after review, there's multiple perspectives on whether the issue information is helpful to consumers of the CVE list. Our current preference is in the direction of keeping the CVE ID assignment. There is a valid weakness, integer overflow, it's a CWE, that can lead to a valid security impact, denial of service, based on retrying network traffic much more often than is documented or requested. So if you put a really long retry, and that's a much shorter retry now, and that might not be what you needed, it's a valid vulnerability, they say. And they signed the CVE assignment team. They don't identify a particular individual. Again, Daniel states it is not a denial of service, it's blatant scaremongering and helps absolutely no one to say that it is. So this is kind of what happened. Somebody said, I got a CVE. Daniel said no. And then they said, well, please, can I have a CVE? And somebody else said, okay, we'll give you that CVE. Ultimately, what he ultimately did is he was able to provide a lot of documentation on the website and say, hey, this CVE, like this is my attempt at that CVSS score, came up with like barely like a 3.3. It's basically a low. It's not even a thing. But it still exists. It's not even listed as disputed. That's your vulnerability. And this is the kind of thing that is important to know about and take into context when we're looking at if you have an automated scanner that goes into repositories, identifies some code, and then looks up CVEs associated with that, pulls back this big long list of, well, some of those vulnerabilities are going to be this nonsense. And that's it. So you cannot just take this stuff at face values. Not all vulnerabilities are vulnerabilities. Not all vulnerabilities are vulnerabilities that you care about or that affect your system. Yes. Excellent. Perfect. When I made that slide about a week ago, it wasn't. Okay. Well then, my source it wasn't. I was looking at older data. Because again, I was basically just basing it off of the story. So let's look at another vulnerability. CVE 2023-39848. This is a SQL injection in the username parameter of a login function on a website. That website is the damn vulnerable web application. This is a GitHub project that's specifically to provide vulnerable applications so that people can test things out and learn about how to exploit these vulnerabilities, how to detect them. So somebody filed a CVE for this, or somebody filed a vulnerability report for this. It was initially assigned a CVE number. This one, it absolutely has been, it's like you go to this all over the place. I think it only lasted for about an hour before people said, no, this is ridiculous. But a lot of pen testers were saying, we're really excited because they're like, hey, next time I go on a gig and I can't find a vulnerability, I'll just pop this up and say, hey, I found a vulnerability in this application I just wrote. But yeah, so this one is absolutely rejected. But it gives, like, people do the best that they absolutely can, but stuff like this is going to happen. Like, it's a system. It involves people. It involves trust to understand different contexts and different understanding of what vulnerability is and isn't. And you can't just take this stuff and say, oh, I've got a CVE, therefore it's a vulnerability. It might be a vulnerability to somebody, but okay. So that's getting into science. Now we get into the more interesting part in the art. I think this is a fantastic vulnerability. I don't know that there's a CVE associated with it, but it does get to the point. We have an urgent recall of Paw Patrol snacks from the company that makes Paw Patrol snacks. The issue at hand is that a website URL published on the packaging has been compromised and contains explicit content unsuitable for children. Please return your snacks to the company for a full refund. So this isn't a cybersecurity vulnerability. Like, this is something that's affecting a real company. And what I suspect happened is that they probably had a domain, they didn't renew that domain, and somebody saw it and then they grabbed it. They have control over that domain now. And legally, like, there's nothing they can do about it. They let it expire. And so, like, this is their only recourse. They have their products up, they published it, it's on their products, and now it's hosting this explicit material, but their products are still out there. They've got a shelf life of, 5 years, 10 years, I don't know, whatever it is. Probably only 6 months, but ultimately, this is a vulnerability. Somebody's posting a web link on their packaging. It does involve cyber because it involves computers and all that kind of stuff, but there you go. So I'm going to go through another vulnerability example that I think is pretty fun. You can find this description on exploits.forsale. It's been given the fun title theme lead because giving vulnerabilities names is all the vogue. And it's arbitrary code execution via Windows themes by Gabe K. So some background. This is on Windows 11 specifically. So on Windows, .theme files allow customization of the OS appearance. The theme files themselves are INI files, so there's text configuration files. So you can just read them and edit them with the text editor. And it contains configuration details. Clicking on the theme Windows file will invoke the following command. It will call run DLL using a DLL called themescpl.dll, call the function openThemeAction with the name of the theme that you provided. So that's what happens in the background when you double click on that. You could also just run this on a command line, but when you click on things, magic happens. The vulnerability specifically deals with the handling of .ms styles files. They are dynamically linked DLLs, files that contain resources to be used in the theme, but should not contain code. That should is important because, of course, it can contain code because it's a DLL. An MS styles file can be referenced in the .theme file in the following way. So this is just a section inside that .ini file, which is just that .theme file, and it just has a reference to visual styles and has a path to the MS styles file. So when you open the .theme file, all referenced MS. When you open that MS styles file, the load theme library and another library will check the version of that theme, and we'll do this by loading a resource called pack theme version from the binary. If the version it reads is 999, it will then call into another function, revised version if necessary. I'm not going to provide the decompiled version. We just know that it checks for a version. If it reads 999, it's going to call this other function, revised version if necessary. Revised version if necessary happens to allow a signature bypass because of a vulnerability, time to check, time use, also known as TUCTAU. What it does is it needs to do some verification. So given a path to an MS styles file with that 999 version, it's going to create a new path by appending underbar vrf.dll to the file path. It's going to check if that exists. If it doesn't exist, it stops. But if it does exist, it's going to open that. It's going to verify the signature on that to make sure it's signed by a certificate code signing authority that Microsoft trusts. And then if the signature is invalid, so if I just provide random DLL, it's going to quit. But if the signature passes, then it's going to close the file, and then it's going to load it again and actually call the verify theme version function inside of it. So this is a time of check, time of use vulnerability because in steps 1 through 5, it's doing the time of check. It's validating a signature, and then it closes that file. And there's a brief window of time when if an attacker has access to that file, they can replace it with a different file. And then when that gets loaded up the second time, it's now not the file that was verified. And there's another issue here. It's called the markup web bypass. So if you've ever downloaded a application from, or like a PDF or a presentation or some files from the web, and you double-click on it to open it, and this happens on Windows and Mac OS and a lot of other operating systems, it'll say, hey, this came from the internet. Do you really want to do this? And then you can say yes or no, because maybe you accidentally clicked on it or whatever. That's called mark of the web. So when you download things over the web, your operating system will say, or your browser will say, hey, this came from the web. Don't just open it. Like, put another barrier in place. So if a user downloads this .theme file, it applies that mark of the web to it. So that when you double-click on that theme file, it'll say, hey, do you really need to do this? So that'll stop somebody from accidentally executing code that they didn't mean to. But that doesn't happen for theme pack files. So if you take your theme and you put it in a cabinet file, to the Windows compression type file, then there is no mark of the web. The execution of the theme, all the steps that we previously described will still happen, trigger automatically, and now you've got your bypass and mark of the web. So they developed a proof of concept for this, where you can have a theme file, and that theme file will reference a MS styles file, and the MS styles file will have a path, and that path can be on an SMB file share. So it can be on a remote network. So I can just set up as an attacker, set up my SMB server, and have my MS style file there. I can have that special DLL that's checking for the version, and then once the server connects to me, reads that, verifies the signature, I can then replace it with now my code that I want the system to execute. And that going over SMB is important for a couple of reasons, because one, it means I don't have to have code execution on your server to actually replace the files to take advantage of that TUCTAU vulnerability. The second thing is it also gives me more time, because networks are slow, even fast networks are slow. So that means that I can see you do the check, and then I can very quickly swap it around as soon as I see the close. There's probably some other things that you can do in terms of file locking for SMB, but ultimately it's very, very easy, very usable. It also means that I can just send you a theme pack file, and you just open it, and now all of a sudden I've got code execution on your machine. Very much a vulnerability. And he provided the proof of concept down there, which you can use and actually play with if you're interested. So this guy actually used to work for Microsoft. He was just looking into these weird theme files as kind of a fun project. He reported it and submitted a POC. Within 2 days, they said, yep, that's a vulnerability, gave him a $5,000 bounty. And then just a little over a week ago, they released a patch. So the patch is interesting. So when Microsoft released the patch, what they did is that they removed that version 999 functionality check entirely. So that mitigates this very specific exploit, but it does not address the one and only actual vulnerability in the whole process, that tactile vulnerability. That's still there. But it kind of doesn't matter, because we've got this other thing that was actually causing that to happen. So you have these sequence of events. And every one of these sequence of events and all these technologies and the reasons why the computer is doing these things is for reasons entirely outside of the specific functionality of this vulnerability. It's to do something else. Like when you load a theme file, you have these assets stored in DLLs. That's done for a reason. When you load and those get stored as DLLs for a reason. Accessing remote shares automatically, if you just have the path that's a remote share, that's also done automatically for a reason. It's features built into the system. And that's another interesting thing about vulnerabilities, or at least about computers, is that it used to be, in the early days, that the more complicated your computer was, the more expensive it was. Now we're getting to the point where complexity is cheap, and it's not only cheap, but it's cheaper than single-purpose computers. If I want to buy an ARM chip that has every last gadget, every last wireless protocol in it, supports all the things, does a million other different things, that's going to cost like maybe 5 cents or a quarter. If I want to have a custom-built ASIC, application-specific IC, that only does exactly one thing, that's going to be astronomically more expensive, like orders of magnitude, because you have to design it, you have to fab it, you have to build it, whereas the ARM chips are just popping out all the time. So complexity is cheap, and it exists on the system. 60, 70 years of computer history, we have inherited and we keep building upon and building upon and building upon and building upon, and we have 70 years of decisions and constraints that we now have to live with, and they're all in the system and they're all just there. And so the art of vulnerability is somebody who goes, hey, this is an interesting theme file. What happens if? And then they start playing with that. And they start saying, well, okay, we've got this weird MS styles file. Like, what does that do? Oh, that's a DLL. What happens when that DLL gets loaded? Oh, it checks for this version. That's strange. Well, what if it checks for that version and it executes code inside of it. Well, that's cool. Can I control that code? Well, I can only control that code if, and then you just start going down this path and this sequence of events. And really, like, that's the art of it, is thinking about what can I do? What do I know about? What's available to me? How do I use that? So I made a promise in the description of the talk that I would tell you how to find vulnerabilities, and here you go. It's easy. All you have to do is look for them. And that is absolutely true. When people ask me, how do I find vulnerabilities? Like, that's literally what I say. Well, I look for them. How do I look for them? Well, I say, hey, I'm an attacker. I have access to these things. What can I do? I say, I can control this file. Okay. I can send this packet. Okay. What does the system do when it gets that packet? Reads that file. And then you start following it down the world of possibilities until you've identified a security boundary that you care about. And as soon as you've identified that security boundary, and you get that mix-up, now you've got a vulnerability. That's my version. Smarter people than I have talked about it as well. Ultimately, it's what we call a tale of two cities. Quoting Chompy again, she says, if you're not experiencing demoralizing levels of failure, you're not doing research. I think this is also extremely true. One of the things that I did not like about consulting is being provided with a system that I've never seen before, using protocols and technologies that I don't even know how to pronounce, and saying, okay, you've got 3 days. Have fun. Find the vulnerabilities or you're not doing your job. There was lots of demoralizing levels of failure in that, but fortunately, I always found a vulnerability. Sometimes that vulnerability is kind of close to that one in the damn vulnerable web application type thing. But usually what you do is you go through and you say, okay, that's technically a vulnerability, but it doesn't matter, so I'm just going to write that down, and then if I don't find anything else, that's what I'm going to report. That's kind of how you do it. Because again, these vulnerabilities are all over the place. The other idea, or the other city, is Dave Eitel. He says that when hackers tell me it's so hard to find bugs, I tell them to stop looking for hard bugs. Specifically, what he's talking about is you should be targeting enterprise software. Because you know how bugs are in enterprise software? A lot. Why? Because enterprise software is really to have a few $100,000 just to start playing with it. You have to have 3 months of training in order to set it up and to configure it and create all the dependencies and all that kind of stuff. You have to have an enterprise to use enterprise software. But if you can start targeting enterprise software, if you can get access to that stuff, really, really basic vulnerabilities. You might say the same could be true of industrial control systems. From my experience, that's kind of true, but also not true. The kind of true part is that hacking industrial control systems, when I started doing it, we used to joke that like hacking ICS is like hacking in the 90s. There's no protections. You get a buffer overflow. You don't have to bypass ASLR. You don't have to do DEP. You just win automatically. Quite famously, there's the idea of vulnerabilities that you identify, something like memcopy over TCP, where one computer has a protocol. You talk that protocol. You can say, hey, copy these bytes to that area in memory, please. And it's like, cool, I'll do it. Easiest code execution ever. But on the other side, again, we're talking about implicit and explicit security boundaries. If you can talk to an ICS device, you're supposed to be able to talk to it. The boundary does not exist in the device itself. It exists in the world around it, in limiting networks. And that's how it's existed for a long time. When these devices were built 20, 30 years ago, because they have 25-year lifespans, nothing was connected that way. If you were on the network, you were supposed to be on the network. It's only when you take that security context that it was designed in and you start connecting it into new contexts that you have problems. I also made another foolish promise to tell you how to fix vulnerabilities. So now we go to the famous scene where Who Killed Monty Burns? This was running when I was a kid. And basically there's a great tie-in with Butterfingers, and I liked Butterfingers at the time, so anyway. The idea is that like, for some vulnerabilities, it literally is like taking candy from a baby. Babies have this weird vulnerability in that they're not very strong, and you can just take things from them. Why doesn't this happen more often? Well, we've got a defense mechanism against this as a society, and that might be just called kind of like shame. If somebody's walking around literally stealing candy from a baby, I don't want to be around that person. I'm like, hey, that's a really crappy thing to do. Why did you do that? The baby's crying now. I can't get that kid to go to sleep. Like, I just got 2 hours sleep last night. You took the candy that I gave to my baby to get that kid to be quiet, and now it's gone, and she's screaming again, and so on and so forth. Shame is a defense. Shame is a mitigation. Fixing vulnerabilities requires an understanding of what is the vulnerability, what is required to get to it, and understanding the core of the vulnerability tells you how to fix it. It's not just patching. When people talk about defense in depth, they do not mean have multiple firewalls in place. They mean provide multiple types of defenses and think about what is going on here. I can't stop adults from stealing candy from babies, but I can shame them. I can say, hey, don't do that. We can create laws that say stealing is illegal, and then we can punish people when they do it, at least in theory. And that can also be abused. People who don't do things used against them. So in terms of how do you fix vulnerabilities, we have to understand what the vulnerability is and understand that there's more than one. Oh, I'm going along. Okay, so philosophy. I asked my daughter to draw a picture of hacker philosophy, and she said, I don't know what that, what does that look like? Security is a relational property. That means that it only exists in relation to something else. Security does not exist on its own. It's not an intrinsic property. Relational properties are things like I am next to this monitor. It's a property that exists. I can move over here now. It's no longer true. And then I come back over here. It's true again. Security and vulnerabilities are the exact same way. There's no just secure. Nothing is just secure. Everything is secure from something, and it's secure from that thing at a particular point in time. And not only is it a relational property, but it's a property assigned by people. Security is something that we ascribe to these systems. The computer is just a dumb computer, quite literally. It's only secure because I want it to be secure, and I define what that means. Every system owner, from the ice cream shop to the bank to Google to the university, all these different organizations are made up of people deciding what security means. Some people, like people who write applications like the damn vulnerable web application, they're designing an intentionally vulnerable system. If you exploit that system, that's a win for them, that's a win for you. You start to learn how these things work. That is the purpose of the system. If it doesn't do that, then it's not doing what it means. So it means that it's not secure. And now I'll talk a little bit about malware. Given that everything is relational, given that everything is, that security is a property that we assign to these things, malware is the same. Malware means bad software. Who decides it's bad? People do. I decide that any ad that I see is malware. So if you want to really get good at malware detection, just start detecting advertisements. And if you can block every single ad, I will pay money for that. Because again, I decide what good and bad means. Other people decide what good and bad means. So if you're talking about like automating malware detection, well, to some extent, you're trying to automate the identification of what people say is good and bad. And again, there's some science to this. Some bad programs, as a classification, like ransomware, spyware, like they have very specific traits, and we can study those and we can learn it. But to capture it as a whole is ludicrous. So in conclusion, cyber means computery. It does not mean anything else. There's no magic there. The security, and it ultimately means the security system with a computer in it. Computers are everywhere and in everything. You even get into computers these days with your car. So computers are no longer a thing that kind of exists on the periphery. It affects every aspect of our life. Therefore, everything is cyber, literally everything. Therefore, nothing is cyber. So just focus on the vulnerabilities. That's it. Original art done by my daughter, who wishes to go by the artist name Panda.
We've got a few minutes for questions. Jason?
Just a comment. I was talking about Linus Torvalds' idea. He didn't classify anything as vulnerabilities. They're just bugs.
Yep.
Part of that was he didn't want to give any more. He didn't want to make it look any more sexy. You could get root versus to fix a bug process.
Yep. Yep, and that actually works really well in favor in terms of the kernel. Something that is highly intricate, is changing continuously and rapidly all the time. If you have this whole separate bug tracking thing where it's like, that's a vulnerability, that's a CVE, it gets assigned to a single branch, which is then fixed the next day. Like, it's moving so fast that like things are getting patched, and like you can't really keep track of that. It's another bug, we fixed it, let's keep going.
There are other vulnerabilities around web.
Yes, absolutely. No. Well, the food one, that's an example of vulnerability, it's not a bug. Yes?
For an example of that, hard-coded backdoor in a router.
Yeah, it's a vulnerability. It's working as it's intended. They're definitely a vulnerability.
And I guess that's the question, right? If it's intended by the vendor, but not the expectation of the user, is it or is it not a vulnerability?
Exactly, context. So in a lot of ICS stuff, you might have something that's built in to allow the vendor to fix things. They say, okay, we're going to set up this procedure. We know, like, when we're using it, we know what we're doing. And we're going to protect it because we don't want people to stumble upon it accidentally. So it's supposed to be there. It's serving a function. And somebody else looks at it and pulls the firmware off and goes, oh, if you knock it like this, it just opens up for you. Now it's a vulnerability. But it's all about that context.
So Robert, we're hearing a lot right now that memory-safe languages are going to change the vulnerability landscape and reduce significantly the amount of consumer-owned vulnerability in the digital ecosphere. What's your take on that?
I think it's going to help. I think a lot of the help that's going to do is already kind of done in a lot of cases. But again, like if we start to eliminate those kinds of classes, that definitely helps. But is that going to solve the problem? Absolutely not. Is it going to scratch the problem? It's going to tickle it a little bit. But it's all context. It's all who has control. What is that control being used for? Technology is an amplifier. Luddites famously, if you know about the Luddites, you probably know them to be anti-technology. The Luddites were not anti-technology. They were anti-what technology was being used for. So they were very technologically minded, and as these new automation machines, I don't remember what kind of machines they were, like printing presses or looms. Yeah, so I started to get these looms, and they start getting used. You didn't have to have a trained artisan to do it. You could literally have a 4-year-old do it. And so the owners of the factories were hiring 4-year-olds to do it, and those 4-year-olds were getting maimed. And the actual artisans were like, hey, that's bad. So it's not that technology is bad. It's a question of what is technology used for and who is it used against. That's what the Luddites were talking about, and I think we are very much approaching the same kind of world where technology is an amplifier. Technology can be used for us to our benefit or can be used against us to hold us down or whatever it is you want to think about. So yeah. Yes?
I have two things. The first one is, one of to sort of build on what Ginger asked in your response. I think the value of, so when bringing it into dialogue for like normal people. Like we're talking about memory safe languages at a cybersecurity conference with a lot of students and a lot of career changers and people who are not deeply in the research. We're not 100% all researchers here. So to me, some of the value of talking about it so widely, even though it does just scratch the surface, is bringing these issues into like common dialogue so that we are more agile when it comes time to start solving harder problems.
Yes.
To me, like just bringing it to the level of being discussed at a cybersecurity conference that crosses like the technical sort of threshold between like you've got people who are still in their education, you've got people who are changing careers, you've got people who have been doing this for 30 years. I think there's a lot of value in that and sort of like democratizing the issue in general. So I'm glad it comes up even though it does just scratch the surface.
No, I agree. And to build upon that, there was recent commentary that I saw on Mastodon talking about like that gap. So like I'm talking about, hey, I graduated college in 2000, like early 2000s. I've got 20 years experience in this. There's people who've got 30, 40 years experience in this. And it's very easy to forget that like even the culture, even to say like, this hacker's code hacked the planet. There's people who weren't even born when that came out, and they are now doing this stuff. Like the culture of hacking, the culture of what it is, what it's using, like you have an entirely new generation that who were not brought up with this kind of thing. They're not even thinking about it. They just know, vulnerabilities I can get popped and this kind of stuff. So I agree 100%. There is value in that, especially in education, especially given those kind of generational gaps.
And then one other thing I wanted to say, and if other people have questions, I don't want to take the time because I'm going to get in the next hour. But I have some context around that vulnerability that I think is really important.
Yeah, because I only presented that one side of it, for sure.
No, and so it's not specifically about that, but around the same time that vulnerability was submitted for, this is all public information. And
There was another one for Postgres.
Yeah. Well, there's 130 vulnerabilities with the source projects submitted and received CVEs at the same time.
Yeah.
Which correlate back to patch and update notes that will public posted and posted publicly in like GitHub notes and things like that. And so it seems like, if you were to put the pieces together, most likely that someone is looking for like vulnerability related keywords in patching notes and then submitting CVE requests. So to me, that's really interesting to understand like where is the breakdown of the CVE assignment process there. Is it
Right.
in the researcher? Is it in the CVE program itself? Is it in how we understand vulnerabilities? I would argue that is an execution of the CVE program itself, most likely, because it's a validation
Right. And again, like we have, this is all about systems with computers in it. And that's a system that has computers in it. And the number of CVEs that come up, it's now what, like 30,000 a year? Who's going to validate those things in often incredibly difficult areas? Like it takes time, it takes money, it takes expertise. It's not easy.
Would you like to have 4 digits?
Yes.